Alrighty, happy Thursday here. How you folks doing? Let's do, oh perfect, we just got it just in time. So, I didn't work on this anymore, I promise, but I really wanted to.
Another thing for like you're in bed and you're like, I know how to do it.
I looked at my last solution. So two things went wrong. The first one, when we were looping inside of solve, was definitely wrong because solve is already essentially that loop for us, right? As we're doing this backtracking, we're calling solve over and over and over. We don't need to loop through every possible position in solve. So where we changed it here to say, okay, let's go with the current row and index where we currently are. This is a nice approach here. This is really good. And then what we were missing here was just advancing on a space that was taken already. So our only check was saying, hey, if it is open, let's go do something. So then if it's not open, then our else, where is that? It's going to line up down here, right? So this is, if it's not open, we just need to go advance. And really, we have this code in here to advance. I don't want to have to do this twice, right? So I want to make this a helper method. If I have the same code twice, I should feel bad about myself. That's your general rule of thumb. So I'm going to take all of this and I'm going to pull it out as a separate method. So you can right click, go to refactor, and you want to extract method. And then we can say, hey, this is, I don't know what, advance row call or row column. And then we get a cool method, a self method here, and we're marking it as private. No one should be calling this from outside of the solver class. Right? This is just internal for us so that I don't have to have the same code twice. And then if the space is not open, let's just advance. Go to the next row and column. And I think this ought to fix it. This was undoing, should be perfectly fine. And now we'll take a look. So I'm going to cross my fingers and try it here. I think we had a bunch of extra prints in there too, though, didn't we? Okay, so we get a solution here. And it's crashing, yeah, list index out of range. So in our can place row, it's our method here, we didn't bother to check if row index was valid. So our advancing here advanced us after we got to 9.0, right? We got through the last position. We filled in the very last number here. Now we went to a row index 9, and there is no row index 9. But that was no good. So we need to just double check here in our if we can place that the row index is less than the length of self.board, right? And the number's not in. So make sure it's a valid index and the number's not in there. So this should stop me before I even try and get to that invalid row. So we're fixing column indexes already, right? Our column index we're checking. If we went too far, reset back. But we didn't have any checks for rows because we never had this idea of just advancing forever and ever and ever and ever before. So I think now if we run it, so that was like a 3-line fix then, right? We ought to get a solution. And so this was what we were kind of doing for debugging. We were printing it out every step of the way to see what it was doing. So let's go take those prints out here. Yeah, so we printed if the row index was greater than 8. Yeah, this was printing here we can get rid of. Or do you want to just leave them commented maybe? So I can just comment them out. When we're debugging, something like that. I don't know if that's more useful to leave it in or not. So let's try one more time. Oh, I think we still printed it too many times. So we ran it and then we printed it. So one more time, we don't need this one either. Now we should just get a single solved Sudoku board. And there we go. So given this board here, we're able to go and solve it. So a 1, a 2, a 3, a 4, a 5, a 6, 7, 8, and 9. That one looks good. I don't think we need to check every single one of these, but so that's the idea here. So the recursive method here is what's doing the loop for us. Right? We just need to know what's the next location. So again, that idea, are we at a base case? right? The base case for us was either it is solved. So if it is solved, there's nothing to do. We're just done. We win, right? So if it's not solved, can we take a complex case and approach the base case? And that was, okay, let's put a number in. We're just going to try a number. This idea of backtracking is saying we're going to go through and we're just going to try something, put it in, and then recurse. If we come back from the recursion and we haven't solved it, we're going to go undo what we did. Undo what we did, put the blank back in, and then the loop says, okay, I'll just try the next number. So the undo step here, it's going to try a 1, it'll try a 2. It never had to try anything past 2 because we found a solution right away, right? But we know for this one, there always is a solution. So I only have to try the numbers 1 through 9. One of the numbers 1 through 9 here will be in the solution, right? There's no, like with the maze, we had to backtrack and say, hey, this was a dead end. There was no dead end. There was just saying, okay, that number didn't work. Let's try the next number. So it's a slightly different idea, but it's still that backtracking process where we're going to take a step, see if we reach the end. Take a step, see if we reach the end. And if we get stuck, that's our other base case. There are no more valid moves. That's a base case. We just need to undo and step back, undo and step back, undo until we can try the next one. So backtracking is definitely not the most efficient way of solving things, right? Because we're literally going out and trying every single possibility until we find one that works. So for maze solving, it's not great. The whole intelligent maze solving and pathfinding is really interesting. It's one of like a basic studies they do in Intro to AI sort of class. There's all sort of interesting algorithms around how do we solve mazes, which seems kind of silly, but like it's the same idea that I'm going to take a complex problem and approach it in a couple different intelligent ways that we can go through and solve these things. So someone actually had a really cool like animated maze solver that uses a couple of the different popular techniques for doing that sort of thing. It's really neat. So that sort of stuff's really fun. Yeah.
What does the
Oh, so this is how do I represent myself as a string? So we're overriding the string function. So I can just say, hey, I want to essentially print will automatically try and turn you into a string. So if I don't have that here, so if we comment that one out here, and I print a class, you get the name of the class, Sudoku solver. It's an object at, here's the memory address. It's not very useful for printing. So like you can have your own method that would give you back a string, but a very common approach is to say, I'm just going to override the string function here. Because we actually get this from the object class, and we'll talk more about that. And we talk about inheritance. So everything is an object. So this is the object version of string. So anything that is an object, which is literally everything, can turn itself into a string, but you get the name of it at a memory address is not very helpful. So we can override that behavior to say, hey, I want you, if you want to have me as a string, I'll give you this string. And we just give ourselves out as like a nicely two-dimensional list here. So that gets called, and then we can actually see the board. That one make sense? Okay, cool. So we're going to try another one here. Let's look at, so there's two chess-related puzzles, which I like, because I'm a big fan of chess. Which, if any of you are bored and want to play on chess, I play on chess.com. I'm happy to do daily games with you, like you make one move a day or something, and that's entertaining. I still actually play daily chess with a student of mine from years ago. I think he works at an insurance company now. Last we chatted. I think that's what it is. I'd have to double check. But chess is lots of fun, and they've got some really cool chess puzzles that are solvable with backtracking. So we're going to do one today, and then we'll save the other one for lab. So I guess you folks can pick. So we can either do the n queens puzzle, and this is a really common. It starts with 8, but it really can be done with any n number. It's not restricted to just 8 here. So for chess pieces, a queen can attack anything on the column, anything in the row, and anything on their diagonal. So the idea is how many ways can you place 8 queens on the board in such a way that no queen threatens any other queen? And it turns out there's actually a lot of solutions. ways of doing this. So we can do a backtracking solution to say, okay, I'll put a queen down. All right, let me try the next one. I'll put it down where I can put it. And we just keep on trying until we can find one that's a solution. So that's a fun one. And this was actually just in the news today. Oh my goodness, what was it? Just had the article. I forget. Somewhere in here. Yeah, here we go. And it's not actually solved. They've made progress on it, which is big news in the math world, apparently. So is this an article? There's no, that's the, oh, that takes us right to the Wikipedia. So this is for n sizes here, what's the number of possible solutions? And he can approximate it to 0.143n to the power of n will be the approximate number of solutions here. It's not precise, but that's about as close as you can get. Apparently it took him 5 years for this, which math just makes me a little bit sad that progress took 5 years, but everyone was really impressed. So apparently that's a big deal. I don't know. Honestly, this level math is just over my head. So, but it was pretty cool. Right? We can make Python solve like 8. I think we got up to like 20 by 20 before it started being super slow. But we can play with that and see how many solutions we can come up with. But we definitely can't make Python do a 1,000,000 by 1,000,000 board. I mean, we could try, but you know, given that it's going to be 5 million digits of solutions, we're not going to compute that, at least on my little laptop here, right? So some solutions are better left to other approaches, but backtracking recursion is a nice, simple approach that gives you a good illustration of why recursion is very powerful, right? Imagine trying to solve Sudoku without recursion. It's doable because, like, essentially this is just a loop, but we have to be tracking every step of the way. It's like, okay, where was the last place that I placed a number? Because then I have to go back to that one, and then I have to go to the next one, and I have to go back and undo. Where by using the solve function here, right, all of the calls, all of those recursive calls are just in that stack there, and Python's tracking, okay, well, this is where I left off. This is where I left off. This is where I left off. So, okay, well, I tried a 3 over here. Okay, I tried a 7 here. Let me go back and undo it. Now I'm going to try the 8. That sort of thing. It will track it for us without us having to manage all of that. So you could. There are iterative solutions to Sudoku solving, but you have to manage that yourself, where this way we let Python do it for us. So that's the n queens puzzle, which was kind of fun. And then there's also the Knight's Tour. Here's another puzzle. Here's our Wikipedia page for this. So the idea is that for any given starting square, a knight on the board moves in a 2x1 or an L shape. And from any given starting square, can you find a path in which it can step on all 64 squares with no repeats? And you can do it from any given starting space, any given starting square. And we can solve it with backtracking recursion. So they got this really cool little animated, here's a solution. And it makes these really cool looking patterns. So that's all. But this is the other one we can solve. So we can do one today, and we can do the other one for lab. I'm open to either. I like them both. What? Queens today? All right, we'll do n queens today. You got it. All right, so we'll solve n queens. So let me start up a new Python file. Again, I like one class per file. It's just what I'm used to. Python could care less. I think it's cleaner, and then it works nicer in source control. But again, you know, that's just my opinion. Other people have other opinions. And when you go out in the workforce, like whoever writes your paycheck, just do what they say, because it really doesn't matter much, right? And it's not worth arguing. Like, don't tell them Eric says I have to put one class per file, because they'll just laugh at you. They'll say, well, Eric's dumb then. That's fine. You can agree. It's just what I like to do. So this is n queens. All right, so we're going to write our class for n queens. Let me zoom this in. N queens here. So now n queens, we're going to build our own empty board. So the board starts empty here. So let me fire up Word here real quick. This actually seems to work easiest for drawing for me. I'd used a different program, and it really made everything lag for some weird reason here. So I think this will probably be good. So again, with our board here, right? We got a chessboard. We have 8 rows and 8 columns. 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. Okay, so we're going to start with an empty board. So we're going to assume it's the 8x8 chessboard to start. We can do this for any n. The algorithm is going to be the same, which is cool. So we say, okay, have I reached the base case? The base case, in the first one we want to look for is I have n queens on the board, right? So are there n queens? And I'm just going to put q here, right? nq. If we've got that, we're done. Check. If we're not, well, how do I simplify this? Well, to simplify it, we put a queen down, right? We place a queen. Right? So we can either go row by row or column by column. It doesn't matter, right? So we can either look at one row at a time or we can look at one column at a time. Either way is perfectly fine. I think columns are easier, but I've solved it most of the ways with columns, going one column at a time versus one row at a time. I don't remember why. Any way should work. So let's just tackle one column at a time, right? So to find where to place the first queen, right, it's the column number equals the number of queens on the board. Right? So how many queens do we have on the board right now? Well, we have 0. So we're at column number 0, right? Index 0, right? Index is 0 through 7, right? So 0, 1, 2, 3, 4, 5, 6, and 7. Okay? So then for every row in that column, right? For the row in the column, really, it's the row in the board at that column, but this is a pseudocode. It's kind of like code where it's kind of sketching out the algorithm flow here, and later we'll go translate it to Python. We'll say for every row in the column, try a queen, right? And how do we know if we can put a queen there? Okay, well, this is then branches out into, we're going to break that down into easier and easier and easier problems. I know there's no queen in this column. Right? That can't happen because we're literally going column by column by column. So I don't need to say, hey, is there already a queen in this column? Because we started with the column number equals the number of queens on the board. So there can't be a queen in this column. Okay, so that one's easy, right? So column is check. That one's done. We have to check the row. Is there a queen in this row? Okay, so we need to go look at the row then and see, is there already a queen here? Okay, that one's fine, right? We can check that one. Then we need to check the diagonals. Right, so the diagonals mean a queen can, so if we were to put a queen here, the queen can threaten anything on this diagonal that way, and then anything on this diagonal that way. Well, there's nothing above the board, so that diagonal is easy, but there's a diagonal down and there's a diagonal up. So we need to look to see if there's a queen preceding me on either of those diagonals. So because we're going column by column by column by column, there's never anything in front of me. I only have to look behind me. Right? So we're only ever looking backwards diagonal up and backwards diagonal down to check if those diagonals are clear, because we're putting them column by column by column. So the way that we're solving this is going to make life easier for us. It's not just, oh, let me just pick a spot on the board randomly, and then I have to deal with forward, backwards, up, left, right, down, circles, I don't know, whatever nonsense. So trying and placing a queen, then we're checking the column. Done. We don't even need to. Checking the row, great. We have to check the row, and then checking diagonal, it's the backwards up and backwards down. Right? If those are clear, if the row is clear, the diagonal up and the diagonal down are clear, we can place the queen. Good. We'll put the queen in, and then we'll recurse. Then we just go back to the top. Right? So at row 0 then, so we're going to say this is our solve here at, we don't even have to tell it anything because it's all based on the number of queens on the board. So just solve then has 0 queens on the board to start. So we're at 0 queens. It says, okay, that first location's open. So we'll call solve again. Sorry, we'll track that. So this is at 0 queens. And then, so what is happening here then in our loop then, we're at row, we're going to try row 0, 1, 2, 3, 4, 5, 6, and 7, right? This loop that says for every row in that column, we're going to try it. So when we're solving with 0 queens, this is 0 queens here, we're going to try row 0. Okay, we did row 0, check. We put a queen here at row 0. Then we're going to call solve again. Sorry, they stack the other way. I'm going down instead of up. Usually we just call them stacking. My stack is upside down, I'm sorry. So now we're solving again. Now we have one queen on the board, and we're going to try row 0, row 1, row 2, row 3, row 4, row 5, row 6, and row 7. So can I put a queen at row 0? No, because there's already a queen in that row. Can I put a queen at row 1? No, because there's a queen backwards diagonal to me. Can't put one there. So 0 is no good, 1's no good, but 2 is okay. So we're going to do 2. We'll put a queen at column 2, or row 2. Why the highlights here are funny. We'll put a queen here. Q. All right, my pen's freaking out. All right, it's an O. Sure, it's an O. Then we're going to solve again. Right, so now we have 2 queens on the board. We're going to check. Can we put it in row 0, 1, 2, 3, 4, 5, 6, and 7? Can't go in 0 because there's already a queen there. Can it go in 1? No, because there's a queen backwards diagonal down of it. So it can't go in 1. It can't go in 2 because there's already a queen in that row. It can't go in 3 because this one's backwards diagonal up of it here. So 4 is okay. So we're going to try it in 4. So we'll put a queen at 4. Queen. Okay, now I can do my Q's letter, so that's weird. Q. All right, and then we're going to call solve again. So then we'll solve. Now we have 3 queens on the board. We're going to try row 0, 1, 2, 3, 4, 5, 6, and 7. All right, row 0 is no good. Row 1 looks like there's nothing in this diagonal, nothing that diagonal. So row 1 is okay. We'll put it at row 1. Okay, so row 0 was no good. We did row 1. Then we're going to solve again. Now we have 4 queens on the board. We're going to try row 0, row 1, row 2, row 3, row 4, row 5, row 6, and row 7. Well, 0's no good, 1's no good, 2's no good, 3. Nothing this diagonal, nothing that diagonal. Let's try row 3. Okay, so 0 was no good, 1 was no good, 2 was no good. We did 3. So I'm marking 3 off because that's the step where we left off. So when we come back to this location with our recursion, we know where to pick up. So then we'll solve. And now we have 5 queens on the board. So we're going to try row 0, 1, 2, 3, 4, 5, 6, and 7 again. Okay, so row 1 is no good, 2 is no good, 3 is no good, 4 is no good, 5 is no good, just because there's already queens in all those rows. 6 is no good, we've got something on the diagonal. 7 is no good because there's this queen on that diagonal. And 8 is no good because there's a queen on this diagonal. None of those are good, right? So solving for 5 queens here, none of them were good. Now we need to come back to our undo step. So if we come back and undo then, right, this comes off the call stack, right? We tried the queen, right? If we come back and we're not solved, undo. Put the queen off of that square. So take the queen off of this space here. So 4 was no good, right? Or 3 was no good. Let's try 4. Can I go in column 4? It's not scrolling. Come on, scroll. There we go. So 0, 1, 2, 3, 4. No, there's something on that row. Can I go at 5? No. Can I go at 6? No. Can I go at 7? Well, 7's okay, right? There's nothing in that backwards diagonal. Okay, so we can try 7. So we've tried all of them here. Okay, so now we're going to solve for 5 queens. We're going to try 0, 1, 2, 3, 4, 5, 6, and 7. All right, we're going to try again. So row 1, no. Row 2, no. Row 3, no. Row 4, no, because of the diagonal. Row 5, no. Row 6, no. Row 7, no. Row 8, no. Well, that didn't work, right? None of these were good. This call comes off the stack here, right? We come back and we undo. Take the queen off of spot 8 here. Oh, we're out of spots. Okay, well, this one was no good then. Undo this one. Take that one off the call stack. Come on, erase. Go back. Okay, so 2 was no good. Let's go on back. You can't be column 2. That was no good. Right, now we keep on going. So that's the backtracking. Oops, sorry, I took out the whole line there. Right? And then we're just going to keep on going over and over and over and over. Right? So that backtracking step here, the trick is undoing. right? Taking the queen back off. So what we've done here, we kind of came up with that algorithm. What is the step by step by step by step that happens? And we just kind of validated it by hand. I don't recommend that for all your solutions. A little bit of sketching through, definitely worthwhile to make sure, like, see if we had any bugs there. If we would have done that with Sudoku first, we probably would have seen that bug where I was looping way too many times or then not moving. My mistake. So definitely we're demonstrating it this time. This is, you know, I'd like to imagine I made the mistake on purpose, but no, I just screwed up. But it's a good illustration, right? We're going to try things and we're going to try and debug our way through it and figure out how it goes. So let's give it a shot. So for queens then, we're going to define our init method. So to make an n queens puzzle, we need to know the number of queens, right? So how many? Well, I'm going to assume it's 8, yeah. You don't have to, no, you can start anywhere you want, but that makes all of my checks a little bit cleaner. And then it's weird because 0, 0 is the top left instead of the origin in Mathland, which would be like the center or the bottom left.
But how will you set like Python to go into a font instead of 0, 0?
I could just pick a different row index or column index.
So you have to pick whatever you want first.
Yeah, so we get a pick. So if we wanted to range from like index 7 down to index 0, we could do that. I'm just going to range from 0 to 7 because it's a little easier. We could tell it to start anywhere we wanted, yeah, and say, hey, pick any one of the 64 squares, put a queen there. But then our algorithm would be a little bit different because it's going to work differently. I mean, it could probably work similar ways, but like because we're tackling one column at a time, it simplifies some of what we're trying to do. Okay, so we can even like default this to 8 and say, okay, if you don't tell me the number of queens, I'll just assume it's 8, right? So then self dot, this is the total queens, or yeah, we'll say total queens is number of queens, and then we'll have a current number of queens. Starts off at 0. So you tell me you want an 8 by 8 chessboard. You want to fit 8 queens onto this board. Okay, that's my total. That's my goal. I'm going to start off with none. Okay, and then we need to build that empty two-dimensional list so that I have places to put all these things. So we had a couple shortcuts for that, but we have essentially the self board, and I'm going to be a little better here. These should all be private attributes, right? We don't want to expose these publicly, so we're going to use this underscore to say, hey, you should not be touching any of these attributes directly, right? Don't go and set the total number of queens here because it's going to mess things up, right? Again, we're trusty because Python will assume you're going to do the right thing. We'll say the board is a list, and then inside of that list, then we need a bunch of other empty lists. And I think we said, was it a list times, and then we just could do a list of, that was going to be times 8 or something like that. I forget. There's some shorthand here for us. I want to say to build out a nice little board here. This ought to do 8 spaces here, and then do that. We wanted that 8 times. Is that right? A list. We want a list. My goodness, I'm forgetting the syntax here. I'll just do this simple. For row in range 8. Oh, this should be range number of queens, right? We'll take self board and we'll append another list. Right, and then for really the column in range number of queens, we'll take self board at the row index, and we'll append an empty space. Hey, Hector, thank you so much for cheering those bits. Another $1 towards the Student Scholarship Fund here at the University of Michigan Dearborn College of Engineering and Computer Science. All right, it's not as much of a deep breath. I feel like I have to like ramp up to say it all on one breath, but thanks so much for following along. So for every row, we're going to append an empty list, and then for every column, we're going to append an empty space. Right? And that'll be a space or a queen. A space or a queen is what we're going to use here for spaces or queens. So that'll set up our board. Again, there's I forget what the short syntax is. You can do it in a single line with like some multiplication, but it'll do the same thing here. Okay, and then we're ready to go, right? So we could either then just call self-solve, or we could make solve be like a method that they can call, But we can call solve ourselves. Like you want to make a puzzle, we'll go solve it initially. So we'll define solve then, given self. So first was the base case, right? If the self.number of queens, our current number of queens, is equal to self.total queens, we reached the base case. How about we just print ourselves? So we need a nice string representation. We're just going to steal this one because it's the same thing, right? It's still a two-dimensional board, so we can just have our own. This is how we show ourselves as a string, right? Just stolen from that one. So if we reach the base case, print. Great. Otherwise, now let's see if we can approach the more simple solution, right? We're going to say for, this is a row index in range self dot total number of queens, total queens, right? This will give me every row, right? Row index 0, row index 1, row index 2, row index 3. Right? We're going to say if self dot can place, oh my goodness, can place queen given the row index, right? Then we'll place the queen. We'll say self.board at the row index at the self.current number of queens. So current number of queens represents the column, right? With a two-dimensional list, it's row, column. So the row is the row we're looking at, and the column is how many queens are on the board. When there's 0 queens, it's column 0. When there's 1 queen, it's column 1. When there's 2 queens, it's column 3. When we have 7 queens, it's column 7. When we have 8 queens, we reached our base case, we're done. Right? Or n in this, right? N, we can solve for any n. We're going to assume it's 8 to start. So we're always going to use that number of queens here. So we place it here. Then we're going to take our self-current number of queens, plus equals 1. We put a queen on the board, count it. Right? And then we recurse, self.solve. If we come back from solve, we need to check to see if we're not solved. So really, this probably wants to be another function here. I'm going to extract this, refactor, extract method. I think, oh, it's not long enough, sorry. This is just one little check here. So we'll say self.isSolved. We can return my number of queens equals total queens. So if self.isSolved, print the self, otherwise solve. So when we're recursing, if we want only one solution and then to stop, we can check if self.isSolved, we're done. So really, if not self-solved, then we need to undo. So if we're not solved, we need to undo that step. So we're going to take my current number of queens down by 1, take the queen off the board, and go back and put the space back. Oops, sorry, we should assign this, right? We should put a queen there. Right? Put a queen in that location, mark that we put a queen there. To undo, take the queen away, uncount the queen, right? Because we're about to take her off the board, take it off the board. So we're just reversing the steps that we did here. Then it'll go to the next row. Right? So if row 2 was no good because we didn't find a solution, undo it. And we should probably check one more time too that we're not solved for every row. Otherwise, we're going to kind of be, if we're not solved and we can place a queen. If we're not solved, then we can place a queen. If we're not solved, we can place a queen. Check every time because we don't want to keep repeating more work than we need to. Because like this will, with that very first queen that we put down, right? If there's a solution where queen is at row 0, when we've hit all the way out to row 7, we placed a queen at row 7 or in column 7. That function, that recursive call will stop, and then it's going to go back to, okay, is not solved, false, so there's no undo, but then it goes back to the next 4. Okay, let me check the next row, the next row, the next row, and it would keep trying again because we didn't check if we were solved or not. We wouldn't be able to place anything, but it's going to do more work than it needs to have to see whether or not we can place the queen. All right, so now we need to figure out can place queen for a given row index. We can define can place queen given self, that was private, right? We wanted to say no one else should do this. So for a given row, and this was 3 different ones, right? We said we were going to return self.can place queen in row given the row index, and self.can place queen, I don't know, or is back. Yeah, these are named funny. How about is row open? And self dot is upward diagonal open, given the row index. And then we'll go one more. Just bump these down. Self dot is downward diagonal open, given the row index. And again, these ones, you need the backslashes for Python to know that that's a multi-line. It doesn't usually like multi-line things. Right? So that can replace here was that combination of those three things. It was, is the column open? We know we don't even have to check because we're only putting it in the column based on the number of queens. So that we're kind of cheating there. Is the row open? We have to check. Is the upward diagonal open? We have to check. And then is the downward diagonal open? We have to check. Right? Always checking backwards. We never need to check in front of us. So we're always checking backwards. We need to solve those three. So a is row open. This one's pretty easy then, given self and a row number, row index, right? And a row index. Row index. We can return self.board at the row index, and if there's a queen there. So the row is open if the queen, oh, sorry, where's the Q character here? Q is not in the board at that row, right? Because board at that row is another list of either spaces, if it's empty, or possibly a queen. So we're going to say, hey, if there's a queen in that row, if there's not a queen in that row, true, we are open. If there is a queen in that row, false, the row is not open. Okay, the logic gets a little bit funny sometimes. You got to say it a couple times to make sure you got it straight. Okay, and yeah.
We can call function for finding, like we call this row open before defining.
I'm just defining here. I think Python will get upset with us. I think they do need to be defined in the right order because it does read it from top down, but we can always move it around after. Yeah, so that's a good point. So those should go above, right? And then we can define our self is upward diagonal open, given self and the row index. Now this one's a little trickier. So is the upward diagonal open? So I know what row I'm starting at. To go up then, I'm subtracting row numbers as I'm going. Right, so I'm going to say for row, I don't know, we'll say like current row in range. We want to start at the row index. We want to get to 0 going by -1. We want to step by -1s. But ranging to 0 is going to stop before we get to 0, right? Ranges stop, right? I'm pretty sure. Let me double check that. Let me just add a new, because honestly, I don't even remember backwards ranges. Print range, we'll go 10 to 0, stepping by -1. Let's double check that. For number in range, print the number. I think it's going to stop before it gets to 0, right? Yep. So if you don't get to the last value in the range. So our range then needs to be to -1, stepping by -1 to get me starting at the row index, going all the way to row index 0, up one at a time. Right? I need to check that. Then what I need to check, right? And actually, I don't need to check my own row index because that's where I'm currently trying to place it, right? We're always going to be one less than that, right? So really, we can start at row index -1. So if you're trying to say, hey, can you put something at row index 2? We don't need to check row index 2 because we're checking the diagonal. We need to check behind it -1. Right, so we're going to start at the current row here, and then we also need to have the current column. So we'll have our current column index is going to be equal to the self dot current number of queens, right? Because we need to say minus a row minus a column. because we're going upwards every time. So when I have one queen on the board, let's see, so we have three queens on the board right now. So we're going to be at column index 3. So if I'm going to check a row index, right, the next column that I want is queens -1, because I'm already in column 3. So I need to go my number of queens -1 to go up 1, back 1. Right? So if I'm checking here, it'll go up 1, back 1. If I'm checking here, up 1, back 1. So same idea then. So that'll be my number of queens -1. And then for my current row, we'll range. You know, I feel like, okay, this might work as a for loop here. I think it'll be easier here if we just say a current row index is row index -1. And then we can do a while loop. We can say while the current row index is greater than or equal to 0, and the current column index is greater than or equal to 0. Right? Because we want to go up 1, back 1, up 1, back 1, up 1, back 1 until we either fall off the top of the board, or we fall off the left side of the board. Or I'm sorry, you guys are facing the other direction here. Right? So to follow that diagonal back up from here, right, we go up, 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 and then we fell off the board at the top. Stop. If we're checking over here, we're going to go up, up, up. We fell off this side of the board. We can stop. So if either the column is less than 0 or the row is less than 0, we can stop. Right? So while those are there, we can say if self.board at the current row index, at the current column index, equals a queen, return false. This is not open, right? Up 1, back 1. If I find a queen, no good. If we don't find a queen, I'm going to take my current row index -1 and the current column index -1. So start with up 1, back 1, check. If it's open, up 1, -1, right? -1 column, -1 row, -1, -1, -1, -1, until we fall off here with the while loop. If we haven't returned false, we can return true. If I have not found a queen and my row index or column index get to be less than 0, there's no queen there in that diagonal. Right? That would make sense. It's a little bit to puzzle through, but that's, I think, the general gist of it here. And now it's almost identical for is downward diagonal open, except now my row is +1, and I want to go as long as my row is less than the self.total queens. Right? So we're going plus rows to go down as we go, or sorry, down and back as we go. We're going plus rows, but still we're going to fall off the column index. So we need to make sure column keeps subtracting, right? Looking backwards columns, but down rows. So now my row index then goes +1 each time. +1 each time, -1 column. So that's for the other direction then. So if I'm going to search downward here, like if I were to look for a queen here, it's plus a row index minus a column, plus a row index minus a column, plus a row index minus a column, plus a row index minus a column. Oops, I fell off the board. Right? Or we could fall off the bottom if we're checking this one over here, right? We'd fall off by rows. Row would be too large here to stop. So it's not the column that stopped us, it's the row that stopped us. So either one of those. And again, we're only having to check backwards because we're always going column by column by column forwards. If we were to just pick a random number, we'd have to pick the forward diagonals and the backwards diagonals up and down. And we'd have to check columns too. So because we've designed it this way, we can cheat a little bit here. Okay, and I think that's it for the diagonals there then. So this ought to print then the first solution here. Because we're saying, okay, if we're solved, stop undoing. There's another step we'll have to do to find all solutions. And we can look at that in a second, if this works. Right, I gotta cross my fingers, right? It didn't go so well last time. I'm hoping I redeem myself here with n queens. Let's give it a shot. So we'll come to, we did main here, we did our no, where did, oh, we did, okay, I just had it in here. This is a little bit ugly to have it in here, but that's fine. I won't feel too bad about it because this is just some examples here. So we'll make a new, I don't know, we'll call this 8 queens here. 8 queens equals an n queens. And I don't even need to tell it size 8 because remember 8 was our default. And it's going to solve itself, right? Because we called solve right off the bat. So it should just solve itself. Let's see what we get. Oh, goodness. Oh, my copy paste for string, we don't have a board that's public, we have a board that is private. Right, that's a bad copy paste. That's me. Let's try it again. Okay, so we get a possible solution. So here's a queen at 0, 0. Nothing in the row, nothing in the column, nothing in the diagonal. Right? Here's the next queen. Nothing in the row, nothing in the column, nothing in the diagonal. Forwards. I'm checking forwards and backwards as we go to like prove it here. Right? Okay, queen here, nothing behind it, nothing below it, nothing in the column, nothing in the row. This queen here, nothing in the diagonal, nothing in the diagonal, nothing in the column, nothing in the row. This queen here, looks okay, looks okay. Open, 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 open. Nothing in the row, nothing in the column. This one here, boom, 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 boom. Nothing there. Rows clear, columns clear. This one here, right? That one looks okay. And then this one here, last one to check. Columns are okay. We didn't hit anything. We found the first solution. Okay, so if we wanted to find all solutions, so actually let me commit this here to GitHub as finding the first solution. I believe there's 96, I want to say, but that's just off the top of my head because it's been a little while. And really, I don't know why that's in my head. Of all the things like I could have in my head, that should not be in there. But I just think the puzzle's really interesting. I made my poor son, he's 14 now, try and do this by hand, and he actually found a solution. He's that stubborn. He's like, and it's not like the hardest thing to do in the world, but it's not the easiest, and it's a little frustrating, but he's very stubborn like me. And he's like, no, Dad, I'm going to solve it. It's like, I can show you how to do it in Python, because he's learning Python. And he's like, no, I'm going to solve it. I'm going to show you I can do it. So I was kind of impressed he found a solution. I'm going to commit these one at a time. So here's Sudoku solved. So you can pick just one item to commit at a time here, if you want. It says Sudoku solver works. Just if you care about the commit history, it doesn't really matter, but as you look back at a repository, you can see individual commits, and you can look at the commit name and see what changed there. So if you can isolate your changes, that's generally a good thing to do. Like it doesn't have to be like a unit of work is a good commit, or just, hey, every hour we're gonna make a commit, that's fine too. Whatever your process is. So this is nqueens works. I think it works. Let's push that. Oh, actually, we should try it for other ends real quick too, before we go and tackle all solutions. So let's try that. So we'll say for, I don't know, queens in range. Now, you can't do 3, I want to say. I don't think there's a possible solution for 3. I think the smallest board, I think it had to be 4, right? Yeah, it's for 4. So if this board of size 4, you can fit 4 queens on there. With size 3, it was impossible. So we'll start at 4, and then let's go up to, I don't know, let's try like 21, see how far we can get. Let's try 8 queens of queens, and I'm going to just print here, so we'll say queens is queens. We can just comma separate. And then I'm just going to print out another empty line just so we get a little bit of spacing in between them here. So let's see if we can get 20 solutions. So 17, 18 is thinking about, it's a little slower, 19, okay, it wasn't too bad, 20, it's a little slower still. Still hasn't solved 20. We'll give it a second. There it goes, there's a solution for 20. That wasn't the slowest thing in the world, right? But it has to do lots of calculations to figure out that. I don't even know how many, we could count all the steps if we cared to. Like anytime we had a call to solve, we could have a counter, right, for step number. And we could just increase that every time solve is called to see how many times solve gets called. That might be fun, right? Let's try it. We can do that. That sounds like fun. So in our init, then we'll have a self dot number of steps. Starts off at 0, and every time we call solve, we'll say self dot number of steps plus equals 1. So when we print ourself, we'll print this plus a new line plus number of steps plus a string of number of steps, self dot number of steps. Number of steps, does that look right? I think so. I think we want this only inside the else though, right? Because solving is not, like once it's solved, that's not a step. So only if it's not solved, we'll count it. Does that make sense? I think that'll work. So let's give it a try. Let's run it again, see. What are we getting here? So let's scroll up a little bit. So 8 steps to solve 4 queens, that's not too bad. 5 steps to solve 5 queens, wow, it's less. So less backtracking, 31. 9 steps for 7, ooh, wow, we got lucky. 113 for 8. So 113 different steps for solve with this backtracking solution. That's not too bad, given that there's 64 spaces on the board, right? 41, so even less with, so is it odd numbers or less then? I don't actually know. This is, I've not tried this before. 102, 52. I feel like it's less for odd. Yeah, it's consistently less for odd. Okay, 1,000, 800, 1,300, yeah, less, okay. 10,000 steps, less, 5,000 steps, okay. 41,000 steps, 19 is 2,500 steps. 20 here, 199,000 steps. So 199,000 different function calls to solve that one with 20. I'm really curious if that pattern stays now. we can look at that another time. But what?
We should plot that.
We could. Ooh, I wonder. Okay. Anyway, and there's a really fun. Was it 3n plus 1 is a popular math thing. Is it Number File? They do really cool math videos, or Veritasium. They do some stuff too. One of them had a cool video about it that I went down the rabbit hole and then looked at, and apparently that's an unsolved math problem. Blows my mind.
I think that one
was a Number File?
I
Okay.
think so, yeah.
They've got the coolest thing. I love numbers. So anyway, cool. So we looked at number of steps. Again, that was fun. Sure. We don't actually need to include that every time though. So we'll how about we exclude that one for now. We'll just go back to the regular board. What if we want to define all solutions now? Right. Well, the trick to finding all solutions is we need a solution count. So self dot number of solutions is 0. And then if we're solved, self dot number of solutions plus equals 1, and we can print out, how about the number of solutions? I don't know if we want to print every time. Maybe we can print every time, and maybe we'll say plus a new line plus solution number plus a string of the solution, self dot solution number of solutions. I think that ought to do it. So this will work, but we need to make sure that we actually do backtrack even if we're solved. So once we found a solution, we still need to undo and see if we can find another solution. Right? So this is where we're not only undoing if we found a solution. So we can find all solutions. So then these just need to get backed up 1. So we're going to try every single possibility. So that very first piece, right? So far we've found there's always been a solution with a queen in that top corner. Right? There was not one of these that didn't have a solution here. So we never tried row index 1 of column 0. Right? We want to get all the way back to the beginning here again and say, okay, sure, let's undo that one too. Let's try the next row. Put a queen here. Now can I find a solution? Okay, put a queen here. Now can I find a solution? Can I put a queen here? Now find a solution. On and on and on and on. Right? So I don't want to do all 20 again here. Let's just do maybe 8 again. Let's just do the 8 again. So we'll do 8 queens. Oh, sure, queens equals n queens here. And we should see, I think it was 96. Is that right? 92. Okay, I was wrong. Okay, I don't feel so bad. So 92 solutions, because there's different rotations. And again, this is super interesting stuff. I think it all makes sense if you think about it, but like if you can solve it this way, if you just mirror it, it's the exact same solution in the other direction. So number of like unique solutions without rotations is separate, and that's, okay, that's beyond us right now. I don't even want to think about how to solve that. So 92 solutions, that was really quick actually, look at that. Solution number 92, which I think follows, right, where now we have the queen in the bottom corner. This should be a mirror of our first solution, I think. Maybe the first, I don't know if it'll be the first, one of the first ones, right? It would be a flip of that very first solution where we had queen here, right? Our first solution, queen there. So is it at, so it'd be at row 5? Yeah, I think that's a flip, right? 1, 5, 1, 4, 7, right? 1, 4, 7. Even if it is or not, it doesn't matter. Sure, that's not really the point. So now we found all possible solutions, right? So one of the things we can do with the backtracking maze solver is we can also find all possible solutions and then say which one is the shortest. Again, not the best way to solve a maze for the shortest possible path, because backtracking literally has to try every single possibility. There's a couple of cool things that we can do there. So do we have our maze solver here? We did a maze solver, didn't we? Or did we not actually code it? We didn't code it. Okay, that's right, we didn't code it. So if we were to code a maze solver then, right, it's a similar idea, right? You give it the board. We're going to try up, down, left, right. That was our algorithm. We'd have to do the same sort of like counting our steps here, where we were doing our step counts, number of steps here. We could count the number of steps, but then when you undo, you have to remove a step. That's part of the undo process. So right now our undo was just take the queen off the board. If we were counting our steps, we would also have to undo the number of steps, because with the maze solver, it was number of moves to get to the solution, not total, like this one was counting total number of times we called solve. Like how complex was our solution finding here? It's a different sort of answer. But we can use that same approach with backtracking and say, okay, let's count our step. When we undo, mark it as the dead end, take a step away. I can find all the possible solutions and then find which one was the shortest possible path. And then a couple fun things you can do there too is once you're on a path that is longer than a known solution or the shortest known solution, you just give it up. It doesn't matter if you can solve from there because we're only looking for the shortest solution, right? So when we looked at that maze, like you could go up, down, around this sort of way. If you found another solution that was shorter and we knew, okay, once you hit 10 steps, there's a solution. If I'm going up this long branch and I get to 10 steps, I'm just going to stop and just start backtracking, right? So there's some optimizations you can do. It's still a terrible solution with backtracking. Again, don't think this is the best, but it works well for illustrating recursion. Oh, and our friend Bay online wants a knock-knock joke. You got it. We have been talking long enough about recursion and mazes and queens and things. We're due for a knock-knock joke. Oh, I got my little nephew with this one. I'm not going to get out of the pack. Actually, it was earlier in the pack. You might remember from last semester then. That's okay. Well, so it's knock-knock. You say, who's there? You say, spell. Spell who? Oh, okay, sure. It's W-H-O. Don't you know how to spell who? That one's kind of like a decent knock-knock joke. He like sat there for a minute on voice. They're playing Fortnite. And he sat there for a minute and he's like, oh. Sweet little guy. I think he's 6 or 7. I forget now. Like time stopped passing in 2020. Do you want a real one then, Bay? Because that might have been a repeat. I'll give you one more. I don't understand that one. All right, maybe you'll get it because I don't get it. Knock knock. Mikey.
Mikey who?
Mikey doesn't work, so help me in, would you? Oh, my key, Mikey, my key. Okay, now I get it. My key doesn't work. Would you help me in? Okay, that was okay. A little bit of a stretch there. All right, so I think we're pretty good on recursion here. The second project we're going to tackle is a recursion project. So in lab, we're going to do the night tour project solution. Bay, that required some high IQ. So we'll do the Knights Tour project. Now that one's actually interesting in that the Knights Tour, the way to solve it, you actually need to go and, if we're going to brute force it here, there's so many possibility ways to do it here. You have to add a little heuristic here. So for our brute forcing here, there's a little trick you can use. Where's that heuristic? Here we go. Nope, that's okay. There's a link somewhere. And the idea here is that your next possible step should be the one. Yeah, here. Oh, is it Wardolph's rule here? Oh, it's right here. Why didn't I find it? Did I spell heuristic wrong? So this Warnsdorf's rule says you want your knight to move so that it'll have the fewest onward moves. So your knight should stay, your first try at it in a brute force attempt should stay near the edges where there are least number of places to move. So if you look at a board here, for any given location, you have so many different moves on the board as a knight. So if you're in a corner, there's only 2 places you can go. If you're near a corner, there's only 3. If you're in the center on an edge, there's only 4. But once you get into the middle, there's 8 different spots you can go. So we're saying if you're going to brute force this thing, stay out of the middle if you can. And once we apply that rule, then it is really quick to solve. If we don't do that, then our computer is going to cry because it's going to try and brute force in, what was it? It had the big number somewhere. Number of directed tours, 19 centillion possible directed tours. Like, and the first path that it tries, like if it gets into the middle, doesn't work. But it has to try every single possible step from there, and every single possible step from there, and every single possible step from there, and it doesn't work very well. So we're not going to count all of them. We won't do the counting here, right? As you can imagine, that would take long. But we'll find one solution here if we can apply the Warnsdorf rule here. In 1984, they were able to solve this here using a computer program. That's kind of cool. That's before I was born, but that's kind of cool. I don't know. Computers are fun. He described it in 1823. How did people do this sort of stuff back then? In 1823, he's like, you know what? I know how to brute force this. I guess people didn't have a lot of like stuff to do back then. I don't know. You're at home bored. Like, was it Newton? No. Was it Newton who invented calculus during the plague? Right? Wasn't it Newton?
Yeah, there was Newton, and I think there was one more person in like Germany doing it
Yeah.
simultaneously.
But like Newton, while he was in quarantine for the Black Plague, invented calculus.
He's like, hey, I have an idea.
So
I want to torture everyone else in the future.
it's amazing, like super cool. There's a calc teacher online who uses Twitch for a lot of things too. Not his classes, but like his office hours. He has his calc students do Python labs. So he gives them a little workbook. He's like, hey, by the way, you know, fill in a couple things here and we'll illustrate some of these calculus concepts. So when he goes through in Calc 1, they're like sum of a is it Calc 1 or Calc 2 where you're getting the sum of an area under a curve and that you break it up with the Riemann's sum and the different rectangles? He's like, we can do that in Python. Here's some rectangles, we'll sum them. All right, here's smaller rectangles, we'll sum them. Here's even smaller rectangles, we'll sum them. Here's 1,000,000 rectangles. Like, and it's just really cool. I was like, you use Python in math class. I'm so jealous. None of my math teachers ever used Python. So I'm a little jealous, but it's okay. All right, so I think we're good for now. We'll come back on Tuesday then, and we'll do the Knight's Tour. So I'll show you a little trick here for this Warnsdorf's rule about how we can stay essentially near the edges. There's a little bit to it there, thing that we can do as we go to solve this. So like in this solve here, we're not just going to do a quick for every possible move. We need a way to sort the next possible moves. So we'll have a way, so given a location, give me the up to 8 possible moves that you can do, and we'll be able to iterate over those in descending order, right? Of least possible next moves to next moves, most possible next moves. We'll talk about that in lab, and it's really fun. And then the next project then, after our Trek Wars is due, will be a recursion-based project. We're going to play with checkers. I don't know, they're all board games, but I like games. So checkers is lots of fun. There's some stuff we can do with checkers and recursion and seeing if we can outsmart the computer sort of thing. Okay, so I think we got this here. This was N Queens. This was counting all solutions. And that's not even spelled right. Counting all, nope. I can't, that's 3 times in a row. Counting, nope, why? All solutions. I would have been faster just to fix the typo.
Is there any way I switch the N and the T on your keyboard? Not getting before class.
All right, so we'll be done a couple minutes early, make up for hanging out late on Tuesday when we couldn't figure out Sudoku. Okay, I made a mistake, I screwed it up, but hopefully that's illustrative of when things don't go well, let's just try and solve them, like and do some troubleshooting, because that's what happens in the real world. That's what I do in my day job. Most of the time is figuring out why my code isn't running right, and then it does run right, so it's always exciting. All right, folks, you take care, and I'll see you on Tuesday.